Yeah, yeah.
More numbers. But still, I mean, if you have capital elections, it's really quite an interesting reflection for high school students about the energy problem. Yesterday, we heard about a miracle in the Middle East, Sesame. And today, we'll be telling us whether future energy needs to be met sustainably.
Okay, thanks, Lewis. So the answer to the question, can future energy needs be met sustainably, is yes. But, you don't leave, please, not as soon as we would like. And in this talk, I'm going to emphasize the buts and draw attention to some elephants in the room. But I hope you won't conclude from that I'm a pessimist about this. I think I'm a realist, and actually I'm becoming an optimistic realist. There are lots of good headlines out there. Let's take 3 from electrical power generation, but they all have to be treated a little bit with caution. It's true that 2015 was for the first time more generating capacity of solar and wind was installed than for fossil fuels. So more capacity was installed for renewables. However, globally in that year, solar was producing at 13% of capacity. Capacity would mean running 24 hours a day. It's obviously impossible for solar with good sunshine. Solar was at 13% globally, wind just below 25%, gas is at 40%, coal is at 60%. So for solar to really catch up with gas, you've got to install it 3 times as fast. It's good that it's being installed faster, but it's not enough. Next good headline is that it's also true that in good conditions, the generating cost of electricity with wind and solar in really good conditions is less than that of gas. But that's not sufficient either, because not all conditions are good, but more than that, for intermittent sources, the cost and the value are not necessarily the same, and there's going to be a cost of accommodating these variable sources. Another piece of remarkable news is that 5 weeks ago today, the 27th of April, was the first day that in the UK no electricity was supplied by burning coal. The first day since 1872. Every day since 1872, coal has been putting power on our grid. Now we had a day with none. Quite remarkable. I could say how that came about a little bit. Now, I want to start with the things that determine energy policy, and they are 3. One is security of supply. It shouldn't be an issue. The world's awash with energy resources, but it is in some places. Let's look at the Ukraine. In the Ukraine, 48% of electricity comes from nuclear power stations which are nearing the end of their lifetime. And the alternative is to get coal and gas, which will either come from eastern Ukraine, which is controlled by Russia, or from Russia itself. So I think that if you were the energy minister in the Ukraine, you'd be quite concerned about security of supply. Cost, of course, is an issue everywhere. And then there's the clean environment. Now, the clean environment, there's a lot of rhetoric, but there's not so many places it's driving policy. Actually, one is China. That's a picture of Beijing, where public demonstrations about pollution have driven policy. Another, rather surprisingly, is the UK, where we have a rather good record on reducing carbon emissions, but we've done it in a very expensive way, got a bit of a mess, and I was really ashamed that our Prime Minister has not joined other European leaders in condemning President Trump from pulling out of the climate change agreement. So I'm a bit worried about the future of our policy. Another country where clean environment is said to drive policy is Germany, with the Energiewende. But in practice, that just means we want renewables. But since they've turned their back on nuclear, they've been building coal, particularly brown coal, lignite, to replace it. And Germany actually has a much worse record on carbon emissions than the UK or than France. But they are, nevertheless, have been leading the way in renewables. So the secret to clean environment is decarbonisation, and I think there are 3 reasons for that. I'm not going to say more now about climate change, though I will in a minute. You've probably heard more than enough about it, especially in the last 24 hours. The second is air pollution. According to the World Health Organization, air pollution causes 4.3 million deaths a year from indoor air pollution, cooking over dirty fuels in the developing world, and 3 million deaths a year from outdoor air pollution. That's 13% of all deaths. Now, when you talk about something causing death, you've got to be a bit careful, because you can't increase the number of deaths. Once you're born, you're going to die. That's a theorem, I think. So what we're talking about is loss of life. So it's important to understand the amount of life that's lost. If you die 5 minutes prematurely, probably nobody cares, unless you were just about to sign your will. But this, as far as I can understand the data, these deaths from air pollution are typically 10 years loss of life. Now, it is mainly a biggest problem in India and China and the developing world, but it's also a problem in the developed world. There's an MIT paper, which I think gets rather too large numbers probably, but they do give an error band, which thinks it's causing, burning fossil fuels is causing 8% of all deaths, also with 10 years loss of life in the USA. The biggest culprit is emissions from cars, followed by power generation and burning coal in industry. And the final reason to decarbonize is improving security of supply, but I think also rebalancing global relations. If we look again at the Ukraine, actually, or rather, let's look at Germany. So Germany relies very heavily on Russian gas for its heating. And I'm sure that that has influenced the German policy towards what Russia is doing in the Ukraine. Germany has been the mildest of all European countries in condemning what's happening in Ukraine, and it's surely because they're relying on their gas. And I believe that if we were not, the US is becoming relatively energy independent with shale oil and shale gas, but most of us rely very heavily on importing oil from the Gulf. And we're kowtowing to some pretty revolting regimes there, which I think we would not be if we did not rely on them. So I think the world will be a happier place without fossil fuels for these three reasons. Now, how are we doing? We should be decarbonizing, but there's a long way to go. So I put a few elephants here to show elephants in the room. The first elephant is that although we talk a lot about wind and solar, and I'm going to sing their virtues later, the fact is that we're still getting something like 80% of our primary energy from fossil fuels. So there's a very, very long way to go. Secondly, it's a moving target. Most predictions think that by 2035, energy use will have gone up something like 30%. Fossil fuels are not going up 30%, but they're expected to go up 20%. They're still going up. They're becoming a lower proportion, but they're growing still. And by the way, most of this growth is in the poorer countries, the non-OECD countries, and it's a good thing. Part of it's a good thing. Energy use by 2035 in non-OECD countries is thought to be going to rise about 50%. 20% of that is due to growing population, but 25% is from more energy per capita. So it's lifting millions of people out of poverty, allowing them not to cook on dirty facilities and die from air pollution. Now, climate change. This graph here, this is produced a few months ago by BP. These are just data. These are billion tons of CO2 emitted each year from the energy sector. So what's this projection? That's their best guess of what's going to happen. And it's difficult. It could be wrong. It's a projection. It will be wrong. But it's difficult for it to be very badly wrong because the infrastructure we're going to be using in this period is mostly in place. What's the red line? The red line is a projection where they've made a model which they call the 450 scenario, where without any consideration of cost or realism, they simply force the energy system to keep the CO2 in the atmosphere below 450 parts per million. That's the level at which the experts say there's a 66% chance temperature will go up less than 2 degrees. So when our leaders say we want to limit the temperature rise to 2 degrees, of course, there's a lot of uncertainty in the connection between CO2 and temperature. I think what they really mean is we'll try to keep below 450 parts per million. Of course, if we're lucky, we might get to 600 parts without going over 2 degrees. But if we're unlucky, we might go over 2 degrees at 300. Anyway, that's the scenario that does it. And the important point is that CO2 accumulates in the atmosphere, so it's the area under this curve, it's the integral that matters. So if we go on this trajectory and start coming down later, we've got to come down faster. And as I already said, it's hard to see this being badly wrong. And my colleagues here, listed here, last year quantified this. I've been saying this, but they actually did some work. And they made the heroic assumption that they looked at power generation. And they made the heroic assumption that every other sector, transport, agriculture, behaved in a way that was necessary to keep below 450 parts per million. And their conclusion was, for the power sector to play its role in this, we must not build any more emitting generation capacity after the end of this year, or retire stuff that exists prematurely, or retrofit it with carbon capture and storage. So to me, that's a quantification of my remark. It's hard to get off that curve badly off it. And I think it shows that it's not impossible to keep for 450 parts per million. I think it's probably impossible at a price that society is willing to pay. Now, there is a global agreement, which has been much in the news in the last 24 hours, about limiting CO2. I've always been a little bit skeptical about this because the agreement asks for something that I don't think can be done, to keep below 2 degrees or keep below 450 ppm. And it goes on to say, let's try and keep below 1.5 degrees. I think it's good that our leaders have that ambition, but I'm worried that if they can have that ambition, which I don't think is realistic, they haven't really understood the difficulty. That will be a concern. The bad thing about the Paris Agreement is that it's entirely voluntary. Each country has to make pledges. But if it hadn't been voluntary, they'd have never reached agreement. So you've got to take the rough with the smooth. There are pledges on the table now, and they're nothing like strong enough. They think they keep us to 3.5 degrees, according to the best climate models. There's another bit, which is that developed countries will finance developing countries to help them move away from emitting sources. Now, what about the US withdrawal? Does it matter? Well, yes, it does, particularly, I think, with this funding of developing countries. But I think it's not really critical necessarily. First of all, the states have a lot of control of energy policy in this country. California has rather strong ambitions in limiting emissions. And secondly, in the end, what's going to get us there is developing alternatives that are as cheap as fossil fuels or cheaper than fossil fuels. That will fix the problem if they're acceptable to people, and I think we're heading in that direction. By the way, even if you don't necessarily subscribe to climate change, you can suffer from it. I don't know if you've seen this picture. This is according to the best predictions of the rise of sea level by 2045. So we will see. Now, ways to decarbonize. There are really three. We can reduce demand. We can build buildings that use natural light. This is a bad example. We can build cities that encourage you to bicycle or walk, and so on. Or we can change our lifestyles. We could all become vegetarians. Hard to make people do that. Or we could use energy more efficiently. That's essential, but it won't solve the problem. There is some good news there, which is that if we look here, from about 1960 to 1990, the world gross domestic product and energy tracked each other. When GDP went up 10%, world energy went up 10%. But since about 1990, they have decoupled. And we're managing to grow economically using energy, less energy. That's good, but the energy is still going up. Carbon dioxide and energy tracked each other up to about here, and they're starting to decouple, but CO2 is still going up. Now, technically, we can do much better, and I could explain, but I'm not going to have time, the reasons it's so difficult to realize the potential savings of energy efficiency, many of which save money as well as energy. And in fact, it's not just a free lunch, it's a lunch they pay you to eat, some of it, but nobody's eating it. So you have to ask why not. And there are a number of reasons for that, which I don't have time to go into. Let me just say that the one thing that really works is regulation. And I'll show you a slide showing that. But then I'll come back to low-carbon sources. That's the other way to decarbonize. So this is quite an interesting graph. It's a bit old now. This shows US passenger vehicles, and two things are plotted here. This is efficiency. This is ton miles per US gallon. And throughout this period, the manufacturers, unfortunately I don't have more recent data, or I haven't bothered to find it, the manufacturers made more and more efficient engines. This is the one that matters. It's miles per gallon. It's on a different scale, but it's also linear, so you can adjust it so it looks the same. So that was also rising linearly, and then it stopped. And the reason was very simple. This line has moved. This was the end of the first set of corporate average fuel economy standards. So the manufacturers, by law, had to make the cars to have better economy. They made better engines, and they had better economy. But the numbers don't mean much, because the manufacturers cheat, of course, the absolute numbers. But the change from year to year does matter. But in this year, they froze at 28.5 miles per gallon. The manufacturers went on making better engines, but they put them into heavier cars with better acceleration. But I think that one graph tells you instantly regulation really works. And these standards, I don't know what Trump's going to do with them, but Obama reintroduced these standards. And it'd be very interesting to see new standards, what the effect is. Okay, so before getting to decarbonization, I'm going to ask a sort of what may seem like a stupid question, which is what to decarbonize. And I want to start with how we use energy. And we distinguish primary energy and final energy. So primary energy has a lot of coal in it. Final energy is what we buy. I doubt there's anybody in this room who's bought any coal recently. When I was young, we had deliveries of coal coming to the house, but no more. The coal is used to make electricity, and that's what we buy. So we can look at either. If we look at final energy, 50%, and we divide its use in, you can cut the cake in any way you like, more or less, but I'm going to cut it saying how much goes into heat. This is space heating, water heating, and industrial process heat. Not the heat that generates electricity, heat that's bought, or gas that's bought. 50% into heat, 30% into transport, 20% into electricity. And in some sense, more goes into heat and transport because some electricity goes into heat and transport. If we track that back to primary energy, it's a little bit different because thanks to the second law of thermodynamics, generating electricity is very inefficient. And refining oil is not that efficient. At the primary energy level, it's basically electricity and heat are the same, and followed by transport. Now, when you go to an energy talk, it's usually about electricity with maybe a little bit about transport. And you can ask why, if heat's actually the key thing. And I think the reason is that, in principle at least, we know how to decarbonize electricity. And heat, it's very, very difficult, so people aren't talking about it. One of the ways to do it, and I'm going to say more about this on a couple more slides, is electrify heat, particularly using heat pumps. But that will put up the difficulty of decarbonizing electricity, because it means we'll use more electricity. Transport, I think we do know how to do. I think we're going to move to electric cars, although it's not obvious to me that they will all be battery-driven. I don't think fuel cells are dead. They may be hydrogen cars, because you can, right now, if you can find the refueling stations, a hydrogen car which will drive you easily to Boston, which your electric car won't, and can be filled up in a couple of minutes, just like with gasoline. I think the only other remark I'll make on this slide is that, in some sense, decarbonizing heat and transport are much more people-sensitive. They're harder. I mean, in the UK, we have companies that guarantee to sell you green electricity, but it doesn't mean anything. You plug your plug in the wall, and the effect's exactly the same. It's just that they bought the power from a low-carbon provider, so you feel good. But it doesn't change your life. But how you drive, if you have a car which, won't go more than 200 miles without 3 hours of recharging, that affects your life, so you may not want to do it. If you start retrofitting heat pumps on your outside wall, you may not like that. So these are harder. Now, I do want to say a couple of things about heat, and I'm going to use the UK as a bad example, or a good example of the problem, but a bad example. The UK, it's cold enough that we need heat, but it's not cold enough that we've taken it seriously. When Scandinavians come to my country, they laugh at really they laugh, so the poor standard of the insulation. So we're sort of muddling by. I think an important thing to say again is that if you ask people in the UK, if you say to them, I want to talk to you about the grid, they immediately assume you mean the electricity grid. But actually, 50% more energy is delivered over the gas grid in the UK than over the electricity grid. That's not including gas that goes into power stations. And it's incredibly seasonal. That's the difficulty. So this graph here, it's a UK graph, this shows the average gas load, and that's the envelope on the coldest days. Now, electricity averages about 38.5 gigawatts through the year. It's also peaked. It goes up to 60 and down to about 20. So when you add, if you simply electrified heating with resistive heaters, not with heat pumps, you'd be adding a peak of the electricity of 60 to a peak of 160. You'd have a system that peaked at 220, but in the summer, most of the year was providing sort of 40 or something. So it will be incredibly expensive. You'd have to have the generating capacity to supply this, and you wouldn't be using it half of the time. So it's tough, and it's also true that gas is much cheaper than electricity. Now, of course, the ways out of this, and this is socially and politically very sensitive. It's very location development, but primarily it's better insulation. Combined heat and power, used a lot in Scandinavia, using the second law of thermodynamics means we lose a lot of heat in power stations. We should be putting it into houses. Electrification. Even if we moved to heat pumps in the UK, we'd still have a very asymmetric system, particularly because older buildings, you'd have to put air source heat pumps, and they're very inefficient when it's cold outside, which is when you need them. So it helps, and we should be putting them in new ones. Geothermal, few places can compete with Iceland. Solar is important in building design, biofuels. Really what we need is seasonal storage, and I'll come back to that. A way of storing electricity from one part of the year to another. And that we don't really have, except possibly using the electricity to generate when there's a surplus to make hydrogen or maybe ammonia, because you can store the gases and then you can put them back again into electricity. As a matter of fact, this is being discussed. There's a big proposal to turn over the city of Leeds in the north of England entirely to hydrogen. Of course, we used to get town gas from burning coal, which was 50% hydrogen, and a lot of the rest was carbon monoxide. It's very dangerous stuff. Now it's a proposal of getting hydrogen from taking North Sea gas, stripping out the carbon dioxide to leave hydrogen, burying the CO2 underground, and then you can store the hydrogen and making underground salt caverns and things like that and putting it into the grid. That will fix the problem, but it's very, very expensive. So this is a big issue and an elephant in the room from my mind. And it's obviously, cooling is an issue too, but not so much. And the part of the reason it's not such a big issue is the parts of the world that need air conditioning tend to have a lot of sunshine. So they'll have a lot of solar energy. So they're very well correlated when you have solar energy and when you need air conditioning. It's nothing like as big a problem as heat. Industrial heat is a major problem because high temperature process heat, melting steel and processes take 1500 degrees, that's not going to be heat pumps. And there are some processes which intrinsically are very carbon dioxide intensive. Making cement, for example. The first thing you do is heat calcium carbonate up to 1500 degrees, and it makes something called clinker, but it drives off CO2. And in fact, cement production is responsible for 5% of the world's CO2. So sort of obviously we should be thinking about capturing that CO2 and burying it, but it will be expensive. I think that our chemical colleagues need to rethink the chemical industry and think of different ways of doing things. And I'm just giving an example which I think is probably unrealistic. But if we look at ammonia production, it's a $100 billion a year industry for making fertilizer. It uses, I think it's 1.5%, 1.4% of the world's fossil fuels, 1.4% of the world's carbon emissions. And again, it starts by getting hydrogen out of gas and then using the Haber-Bosch process. It's very energy intensive. But in principle, and in fact in practice in the lab, you can synthesize ammonia directly from nitrogen, which is all around us, and water, of which we've got plenty. It's very expensive. But if you could do it cheaply, you could, reform the whole ammonia industry. Probably unrealistic. I'm only giving this as an example of the sort of things that academic chemists should be thinking about. And by the way, it's a fantastic storage mechanism. Actually, ammonia has even been used to fuel buses in the war in Belgium. You wouldn't want to do it. It's horrible, nasty, smelly stuff. But if you took the world's supply of ammonia, the current supply, and you fed it into fuel cells, it would produce the world's electricity for 10 days. So if we increased ammonia production by 50%, and we could do it in a carbon neutral way, we've got 5 days of world electricity. So this is wishful thinking, but it's an example of sort of thing we ought to be worrying about. Now, let me come now to electricity. So just to give you a feeling where we get our electricity, I'll show you the US electricity later. This is global. These are International Energy Agency figures and projections. They're projections, so they may not be right. They think that starting in 2014, 67% of the world's electricity came from fossil fuels. They think the world will be increasingly electrified with vehicles and so on, and more electricity in the developing world. They think electricity will go up 50%, 51%. Fossil fuels, not as fast as the total, but still going up. And they still think they'll be dominant at the end of that period, 54%. Hydro can go up. It's going up about the same as the total, according to this projection. Nuclear, quite surprisingly to me, they think is going to go up faster than the total. Wind going up a tremendous amount, but from a very low base. Bio and waste going up, solar, and so on. Now, given that so much of its electricity comes from burning fossil fuels, and it looks as if this is correct, may not be, but if it's correct, we'll still be getting most of our electricity from fossil fuels. The immediate question is, what about capturing the CO2 and burying it underground? Of course, that doesn't deal with the air pollution problem, and it doesn't deal with the security of supply. But if you're only worried about climate change, that can do the trick. The problem is, it's obviously expensive for two reasons. There's the capital cost of fitting whatever carbon capture scheme. There are different technologies, whichever one you want to use. But in addition to that, it takes energy. So if you had a power station, let's say a gas power station, which was 45% efficient, if you made it a CCS, it would go down to something like 35% efficient. So you need more fuel. And it's going to be expensive. These are some numbers from the US Energy Information Administration, which I think are pretty optimistic. And in addition to that, it doesn't capture all the CO2. And the fact is, there are about 2 or 3 trial schemes in the world. To roll this out on a fast enough scale to have a big impact is not going to happen, I don't think, especially as it's so expensive. So I personally think that the place that CCS could play a major role is in industry, because what are you going to do with these 1500 degree type things? CCS can play a role there, but there's no incentive on industry to do it at the moment, anywhere in the world. That will need political decisions to give incentives to people. Okay, let me come now to low carbon sources. And this is a topic on which I want to spend most of my time. So the first question is, are there enough low-carbon sources to replace fossil fuels? And the answer is yes. Certainly there's enough. I mean, there's a lot of them. There's not just wind and solar, there's nuclear, there's hydro, there's biofuels if you're careful, and so on. The second is, can they compete in cost? Because if they were cheaper, that's what we'd be doing. Problem solved. And the answer is, apparently. The generating cost for wind is now the lowest in good conditions, and solar is not far behind. I'll show you some costs in a minute. Though you have to be very careful, because a lot of the costs that are quoted include subsidies and tax credits. And it's very difficult comparing in different parts of the world and what the costs are, and even deciding what is a subsidy, as we'll see. However, and here's another elephant in the room, wind and solar are what are called non-dispatchable sources. That means ones that we can't control. Have to wait for the sun to shine or the wind to blow. And for these, the cost and the value are not necessarily the same. If the wind blows mainly at night when nobody wants the electricity, there's no market for it. And in fact, I believe there's a company, I know there's a company in Texas, where if you sign up with them as your provider, the electricity is free between 10 at night and 6 in the morning. They're giving it away. Because there's, the price is very low, and this bribes you to sign up with them for the rest of the day. So when people calculate, the standard measure of electricity cost is called the levelized cost of electricity generation. And that's got by looking at the capital cost, looking at the operating costs with a proper discount rate and assuming a lifetime, working out the total amount of power you'll get and dividing one by the other. But if some of that power you can't sell, the answer you get is misleading, because you've got a lot in the denominator which you're throwing away. And literally, there are days in many countries, many places, surely in many states now, when there's a lot of wind power, there's no market for it, so they're just told, let it spin, switch off, decouple the generator. Another way of saying that is that if you've got enough installed to meet the average demand, there will be large surpluses at times of high availability and relatively low demand. The other but is that the cost of integrating wind and solar will increase when their contributions increase, for several reasons. There'll still be days, and I'll show you plots of this, where there is no sun and no wind, so you'll need backup. But as you have more and more wind and solar, the days when you need backup get fewer and fewer. But you still got to build the same plant. So it's going to become more and more expensive. And this is happening. One of the problems, or it's a good thing really, that once you've built a solar farm or a wind farm, the marginal cost of producing electricity is zero. So the grid in Germany, for example, says if the wind's blowing and the sun's shining, we will take solar and wind energy. And they say to the conventional generators, get lost. And the utilities in Germany, which invested 20 years ago maybe, not anticipating this, they had a business model which assumed they will sell right through the peak hours. And they are not selling through the peak hours, and they're going bust. The German utilities have lost more money than the banks did in the financial crisis. I mean, it's a really serious problem for them. So we're going to have ways, we've got to have backup, but it's become increasingly expensive as it's used less and less. We'll need better long-distance grid or interconnectors between countries in Europe and in other parts of the world so that we can balance areas with or without the sun shining. But that's not really happening, partly for political reasons. Seeing Luis there, I can't resist saying the weakest international connector for electricity in Europe is across the Pyrenees. And the reason for that is the French nuclear industry don't want to be flooded out with excess, cheap, renewable power from Spain. So they're blocking it. It's a political issue. We need better demand-side measures, having tariffs which encourage people only to use electricity when it's abundant and not when it's scarce. And we're going to need storage, but we don't really have it yet. I'll come back to that. And we're going to need reform of the market to deliver these things, and I will come back to that. Now, I want to now look at the first line here, the abundance of low-carbon sources. Then I'll make a few remarks about some of them, and then I'll come to the cost of wind and solar. So I'm going to start with three that we can display pictorially. So if the sun shone in this area here as much as it does down here, and you filled the whole of that area with no spaces with photovoltaic cells, that will provide all the world's energy. Not just the USA, not just electricity, all the world's energy. So you can see from that solar can in principle power the world. Of course, the problem is, the sun is not shining up here the way it is down here, and it's not shining at night at all. So it's not so simple. It will produce enough power if this was in good conditions, but there's going to be costs of delivering it and so on. This is the area for wind. I've assumed here that the wind blew, if the wind in all of this area, and it's a good area for wind actually, blew as well as it does in the North Sea between the UK and Germany, which has spectacularly good wind conditions, that will be enough to power the world. And there you wouldn't be using up the land. You could have cows grazing underneath. But again, that's always in good conditions. And then this is for bioenergy. If you wanted to grow biocrops, which you then turned into methane or burned or something, to make the world's energy, you'd have to find this area with good soil, good water, and good growing conditions. That would mean we'd all have to stop eating. So that's hard for bioenergy to power the world, but there's a possible get-out-of-jail card. If you're old enough to have played Monopoly, you may remember that. And I'll come to the get-out-of-jail card in a minute. Now let's put that into numbers. So these are the contributions to primary energy, to all energy, not just electricity, from different sources in 2015, in decreasing order. The biggest is biomass and waste, and that's mostly, it's sort of an estimate because there's no market. It's hard to measure this for a lot of this, because this is people burning cow dung in India, burning wood and scrap and stuff like that. But it's very big. Now here we need this huge area, and the problem is, as we've discussed, hydro, 6%, it could triple, but it does have environmental impacts. But there is a potential to increase hydro. Nuclear, there's essentially unlimited potential to increase it. The problem is it's proving to be much more expensive than people had hoped, and there's public perceptions. Wind and solar, the issues of the integration cost. In addition with wind, there's what is a nice acronym, which I don't know if it's used in this country, but in my country, what's called NIMBYism, not in my backyard. I love wind turbines, but I don't want them spoiling my view over Long Island Sound or whatever it is. And that's a serious problem in some places. And then there's geo and marine, which could be important locally, but not globally, so I won't discuss them. Now, I want to just say a couple of words about biomass and nuclear, and then come to the cost of wind and solar. So this is a pretty way out idea, maybe like synthesizing ammonia, but quite interesting. It's being developed by some colleagues of mine with collaborators. And the first is to use a class of plants which are known as CAM plants. It stands for crystallation acid metabolism. I don't even know what that means, but I know how they operate, which grow with very little water. So good examples of this are agave, prickly pear, cacti, euphorbia grows all over Africa. And they're very clever, because in order to photosynthesize, plants need water, they need sunlight, and they need CO2. So most plants, they notice the sun's shining, so they open up and they take in CO2. But if the sun's shining, then they will evaporate. These plants have evolved in dry areas, and they realize that's dumb to open up when the sun's shining. If there's not much water, they'll lose the water. So they open up at night. and they store the CO2 in the form of malic acid. And then when the sun shines, they start photosynthesizing. So that's how these plants can grow at reasonable rates with relatively small amounts of water. And if you could use these plants as an energy source, it means you could use a lot of the world's semi-arid and degraded land. And suddenly, at least on the back of an envelope, it becomes a huge resource. And there are about 15,000 species of these, and they've never been properly researched as energy plants, but it's starting now. Actually, my colleague who's pushing this, who's an entrepreneur who then went into academia, he owns a lot of energy companies in East and West Africa, and he's been trying to grow, this is euphorbia, which grows wild in a lot of Africa. One of the questions is, can you grow it in a way that you can harvest it simply? So he'd been running trials, but the trial got into trouble because there was a dispute about the land ownership, and the people broke in, and they knocked the fences down, the elephants came in. So I can't tell you the result of this test, because the elephants ate the first crop. But this is at a primitive stage. The other idea that they've got is, what do you do with this stuff? So anaerobic digestion, where the process you can throw waste food or agricultural waste or other organic material in tanks, and then it will ferment and it makes methane. Now this is used around the world, but it needs subsidy at the moment. But these people have realized that the rate limiting step in anaerobic digestion is hydrolyzing the cellulose. And it turns out that cows, also kangaroos and some other ruminants, do it 20 times faster than man-made digesters. And they think they know how. Now, they do know how. If they can manage to replicate the way that cows act, and you could speed up anaerobic digestion for a factor of 2 or 3, suddenly a lot of agricultural waste and all this stuff, maybe these plants, become an energy resource at a way that doesn't need subsidy. So this is the sort of thing that I think the academics communities around the world should be thinking about this thing. That's their role, the blue skies thinking. Nuclear, I'm not going to say much. The problem with nuclear is the costs always seem to be higher than people anticipate. And that's partly because the world's not been building, at least the Western world, it's not the same in China and Korea, not been building many nuclear power stations. They're building few very big power stations at intervals. So each one has been effectively like a new project. People haven't really done it before. Meanwhile, the safety people have tinkered with the regulations. The physicists, God help us, got involved and changed the design. And they've all gone over budget. So it's a rather interesting statistic. According to the World Nuclear Association, there are 440 reactors in operation and 60 under construction. But The Economist, which only thinks of 47 under construction, like God knows how they got a different number, claims that 28 of those are behind schedule, which doesn't surprise me, because these are big projects and they're just getting into trouble. Now, in principle, the bigger the reactor, the lower what's called the specific cost, the cost of generating per kilowatt hour. So the tendency has been going to bigger and bigger reactors because they thought the electricity would get cheaper, but the data seems to show it gets more expensive, and that's because they're newer and newer projects. So there's now a thought that if we went to smaller reactors, although on paper that gets more expensive, in fact we can standardize and learn what we're doing. So for example, instead of building one gigawatt reactor, on the same site you might build 5 200 megawatt reactors. And you build the first, and then it's the same people who build the second, the third, the fourth, the fifth. And by the time they get to the third, they know what they're doing, and the cost starts to come down, you hope. It would also reduce the financing costs, because there's colossal upfront borrowing costs. Cost of nuclear is very dependent on the discount rate, because you're borrowing money which you want to get back over 40 years when you sell the electricity. If you can make smaller units, that's not just raising the money becomes easier. The trouble is, I think we should be out there testing small modular reactors, but it's not really being done. There's talk of it in this country. There's some work in my country. But the trouble is, it's not enough to build one. You've got to build 3, 4, 5, 6 and see, is it true? Now, I think the only thing I will say about all new reactors is we should stick to the tried and tested. I hear people saying, I've got a great idea for a small modular thorium reactor. I'm like, oh God. I mean, you know, all new types of reactors get into trouble. And this was recognized actually before many had been built by Admiral Rickover, the father of the US nuclear Navy, who said as early as 1953, an academic reactor is simple, small, cheap, light, can be built quickly, very flexible, very little development, mostly off the shelf, but it's in the study phase and it's not being built. Whereas a real reactor is being built. It's behind schedule, it requires an immense amount of development on trivial items, it's very expensive, it takes a long time to build, it's large, it's heavy, and it's complicated. And this has actually been an incredibly prescient remark, has been borne out, I think. So my belief is we should stick to the simple. The only possible exception to that, and I've not heard much discussion of this, there's a lot of discussion of molten salt reactors. They're usually thinking of molten salt core, in some case coupled with molten salt cooling. But regardless of the core, it's interesting to think of molten salt cooling, because if you have molten salts, they're 1500 degrees or something, you can store the hot salts, and then you could use them to generate power later. So nuclear also has the problem that it's not fully dispatchable. You can ramp it up and down, but that's expensive. What you'd like to do is run it at a steady way around the clock. If you could run it at a steady way around the clock and store the heat in the night and get back power in the day, this would be much more valuable. Okay, I better now get to the real issue I want to discuss, which is wind and solar. So the prices are falling very fast. So just to give some comparison, these are the wholesale electricity prices at different hubs in the USA over the last 2 years. And you can see they're hovering around $35, $40 per megawatt hour. That's 3.5 to 4 cents per megawatt hour. That's the wholesale price. So that's the competition. What's happened to solar and wind? Well, back here, solar was over 200, so how can it compete with 40? Couldn't. Wind up at 50, but they have been rocketing down. Actually, don't fully trust this graph. I think it's not quite that low. But they are becoming competitive. There's no question about it. Now, you've got to be a little bit careful if you go back to the original source of this graph. These include federal and local tax incentives. And when you take them out, it puts the price up. Not by a huge amount, but it does put it up. Here's some different anticipation from the EIA, who every year predict what they think the cost of generation will be for plants being commissioned now but coming online in 5 years' time. And their predictions from month before last is that wind will be at that date at 32, down here somewhere, but that's with incentives. Without the tax incentives, it goes up to 40, but still damn cheap. But that's the best case. This is across the range of the country where it's sensible to build wind at all, and the more higher end, it's up here somewhere. And these are the corresponding figures for solar. So the fact is these costs are still going down. It is becoming competitive, no question about it. The capacity is growing very rapidly, but the role is still small. So this is the generation mix in the USA. And you can see back here in 1990, a lot of coal, some nuclear, some gas, some renewables, some oil. The oil has died. The renewables were mainly hydro. You have to be very careful reading the literature, because sometimes when people say renewables, they exclude hydro, and they don't always say so. And they only mean wind and solar. This includes hydro. This is nuclear, gone up slowly. And look at coal. It was going up, and it's rocketing down. It's rocketing down mainly, partly because renewables have grown, but mainly because of the fracking revolution. Lots of gas. And that's good. Per kilowatt hour, gas produces less particulates in the first place. In the second place, it's about half the amount of CO2 per kilowatt hour. So this is what's happening to the mix. Now, what is the breakdown of these renewables? It's given here. that I found on the DOE website. The trouble is this is per month. So I looked, if you look at 2016, the total generation was 4,080 terawatt hours. On a month, if you just divide by 12, that's 340. Now, if we look here, the average wind, it's around 18, so wind is about 5% now. Solar, much less. It's about 1.3%. That is utility scale solar. There's quite a lot of private solar. It's quite difficult to measure, actually. So I don't know how this was measured or if it's accurate. And, you know, it's significant. It's not as big as the total. It's 1.6, and the utility scale is 4.4, so the total solar is 6. But it is significant. So the point I'm trying to make is that the costs, wait a moment, I've gone too far. The costs are plummeting, but there's a hell of a long way to go. Actually, it's interesting here, this graph, I don't have time to go into it, but it shows you, where it's coming from in the US in a fairly reasonably easy to understand way. Now that's the US. This is for the world, the International Renewable Energy Agency. These are data, so you can see there's a huge spread. That's their average, and this is their prediction. And surprisingly, there are things already on the market below their prediction. And in fact, there's been a recent bid, these are in cents, I think. What are they in? US dollars per kilowatt hour. Okay, so it's 0.03. So there's been a wind bid down here at Morocco somewhere. But that probably has some subsidy in it. I'll come back to that in a minute. But defining subsidy is difficult. This is offshore wind, and that looks quite pessimistic. There's already been a bid at 5 US cents down here somewhere. Now, I just want to make the point, although I've already said it, that you've got to be very, very careful comparing these things. Well, first, why is wind getting so cheap? And for offshore wind, they're going to enormous turbines. Look at this. So we're talking, back here, about 3 to 4 megawatt turbines. Now, for 2019 to 2020, starting to build 15 megawatt turbines. And the size has gone from something like this. The ones that are about to be built now are this size. So that's why one of the reasons it's got cheaper, plus learning economies of scale, et cetera, et cetera. The only point I want to make is that, but the really cheap North Sea bids have been from Germany and Holland, which don't include the connection to the shore. So I've seen headlines in the UK saying, all problems are solved. North Sea wind energy is cheaper than anything on the market. But it isn't, because that's just sold at the platform, the price that was quoted, without the connection to the land or the connection to the grid. So all I'm saying is be very careful with these things. Similar thing with solar, the costs are falling. An important point about solar is the costs 10, 15 years ago were entirely dominated by the PV module, which was falling tremendously rapidly. But now, the PV module for a utility scale solar plant, or indeed one on your roof, is less than half the total cost. So more than half is in the what's called the balance of plant, buying the land, putting up the scaffolding, the inverters that turn DC into AC. That's also falling, but not as rapidly. So I think that curve, which was, economies of scale of making more and more PV, the rest of it's quite labor intensive. It's difficult to see it falling like that in the future. Here again, the PV, there's possible revolutions here, by the way. And again, there's been bids down here. But this one, there's been one recently at 2.7 cents a kilowatt hour. Really, really cheap. But according to the International Energy Agency, if you took out special conditions, in the US this would have been 6 cents. Now those special conditions, it's unclear to me whether you should call them a subsidy or not. That was in the Gulf, I think. And the governments there are saying, we will do the preliminary work, we will tell you where the solar conditions are, and we will guarantee to buy the power for a certain number of years. Now you bid. So they've de-risked it. So here I think they just say, you go out and find the right place. So every company, before it's bidding, it probably hasn't done the full work. So they're taking a risk, so it puts up the cost. And they don't have a guaranteed sale. Now, whether you call this a subsidy or a social investment cost, which brings down the cost for everybody else, is an arguable point. Now, let me conclude on low-carbon sources. The good news is that bio may have bigger potential than thought. There's scope to expand hydro. Nuclear, we must drive down the cost. I think the jury's out on small modular reactors. But the really good news is that, I see that solar bid was in Mexico, actually. The solar and wind have huge potential, and it's falling rapidly. Not so good is that still fossil fuels are at 80%, so there's a long way to go. And the cost of integrating solar and wind will rise as their contributions rise. And it will be necessary to redesign electricity markets. But these problems, as solar and wind get even cheaper, these problems get smaller and smaller. And in fact, it's being turned around now. We used to talk about the cost of integrating solar and wind with the other sources. In some sense, it's the problem of integrating the other sources with solar and wind as they become bigger, which is becoming the problem, which is quite interesting. And countries are now they were subsidizing renewables, solar and wind. They're now having to subsidize conventional generation to provide the backup. And actually, New York State is subsidizing nuclear, I believe, at the moment to keep it running. So the subsidies are moving to keep the rest going. Now, am I going to be allowed to have a few more minutes, Liz? Okay. So on the integrating renewables, I don't have much more. I've got 2 slides. And first, I wanted to show you California and Germany, countries that have gone really big on renewable energy, or states. The first thing is the Germans, it's a very bad place to put wind. That's the capacity factor. I mean, it's producing something like 17% of what it would be if the wind blew round the year, round the clock perfectly. Whereas in California, it's up here at 26%, and solar, it's even worse. This is Germany, that's California. So the Germans, nevertheless, have sort of had the idea, we want this renewable energy. They've paid through the nose for it because lousy capacity factor, but it's given the economies of scale which have brought down the cost. So they've done us all a big favor. Now, here is some of the data in California. This is the wind. These are different wind farms, and you can see they're all fluctuating. But when you add them up, they're relatively smooth. But you see the problem here is that there's a lot of wind at night when nobody wants it, and essentially none in the middle of the day. And I think this is a semi-typical day, and then it rises in the afternoon where there is increasing demand. Solar, on the other hand, is very well correlated with demand, but that's on a sunny day. And if it's not a sunny day, you've got this problem. So you're going to have stuff filling in, and if you're in your own house wanting to be energy independent, you're going to need a big battery. And the solar is being built a lot, but it's producing a midday dip. So this is the need for power in California in 2012 from non-solar sources. And as more and more solar was built, there's a dip in the middle of the day. The solar's there, and it's taking away the market. So we have the problem, who's going to supply the backup for days when there are no sun, because the market's not there. It was very profitable to build solar in California, but now there's so much, there's not much point, because there's enough. It's already made this dip. Now, a curve I understand better, and it's perhaps more instructive, is this one for Germany. This is a model of power in Germany in 2050, made by KPMG, I think. And they assumed this is for January, that's for June. And they took the actual demand, this dark brown curve, or black, whatever it is, that's the actual demand in 2014, and they assumed they got 25% more efficient. So those are data scaled down 25%. And you can see, here's the day and the night, and then here's weekends every 7 days, and so on. And this is the summer demand. Then they said, let's assume in this simple model, there's hydro and biomass, no nuclear because that's a big sin in Germany. running around the world, and around the year. And then they said, let's take the actual data for wind in January 2014 and multiply it by 3. Sort of arbitrary. They could have said multiply it by 4 or 5. Let's assume it goes up threefold. And we'll take the actual solar and multiply by 2. And this is what you find. So the blue is the wind and the orange is the solar. And you see there are times where there's an excess, which you'd have to throw away unless you could store it somehow. And then there are deficits. So to filling the deficit and absorbing the surplus, actually the deficit is bigger than the surplus. But if you push these up, you could actually match the average. But you'd still have no wind and solar on this day or some days here. So what you need is extremely flexible backup. These holes, the white bit that's got to be filled by something else, has to switch on incredibly fast. So there's going to be a huge premium on flexibility with the backup in the future. You need aggressive demand management, tariffs, which encourage people use electricity here or here, but please don't use it here. We need a smarter and larger grid to connect different areas. And we need storage. Now, storage, batteries are sort of okay for dealing with the day-night problem of solar, but they're not okay for dealing with this multi-day problem of wind. And they're certainly not okay for dealing with the seasonal storage, which we'd really like. And there we need something new, like power to gas. This model turned out to be very expensive, but the authors say if you added a bit of nuclear, it would get a lot cheaper. Now, this must be complemented by understanding how to attribute and charge for the benefits of storage and improving the grids, and market reform to deliver what's wanted. I'm coming back to this on the next slide, actually. But with these measures here, we can move to very large amounts of wind and solar. I think very hard to get to zero fossil fuels without long-term storage. But I think, in principle, as the costs come down, we're getting there. I think I'll skip what I was going to say about the supergrid and maybe about storage. Just a word or two about markets. So the underlying problem with electricity markets is that electricity is a very odd commodity. If you're making smartphones, let's say, and you manufacture too many, you store them up and you sell them next month. But if you're making electricity, supply and demand have to match instantaneously. And if you produce too much, you're told by the grid, we don't want it, so it's thrown away. And if you produce too little, huge complaints from the consumers, of course. So it's a very odd market. It's changing very rapidly. We're getting more distributed supply, local supply of wind and solar, new loads, electric cars as they grow. There are environmental targets. And the marginal cost is zero, which is good but not helpful in some ways. And there's a problem that security of supply is something which most people think it's a right that I have electricity. So what are the issues? One of them is how to ensure sufficient capacity for the hour in the year that uses more energy than any other hour. I mean, if it was a totally free market, you'd be crazy to invest a plant that would only be used 1 hour a year. But if you don't do that, there's going to be not enough electricity in that hour. So people are inventing things called capacity markets. But they're different in different places. They're producing distortions and unintended consequences. So the capacity markets have not been great. You need to ensure sufficient conventional generation. As I said, at the moment, nobody is investing in Germany. They're all losing money. And nobody is investing in new gas plants. But they're needed to fill the gaps. The capacity market, which is supposed to help with that, has tended to come out with people building lots of small diesel generators, which are not great for the environment. How to assess who benefits and so on, who should provide the storage, and how do we look at the whole thing in a holistic way? Because if we look at storage, for example, you can make money with storage in two ways if you build a storage plant, by arbitrage, taking off-peak free wind power, say, and selling it on peak, if the sun's not shining, or by providing a balancing service. The grid grids around the world are paying people to help them regulate the frequency when there's a sudden surge or drop in demand or supply. But the amount of money you can make is not anything like as much as the value to the whole system, because everybody would gain from more storage. So we need a new way of thinking about things. By the way, the DOE is having a 60-day study of these issues, which is basically designed to clobber renewables, as far as I can make out. I don't know much about it. I won't say anything more about it. So let me move towards conclusions quite quickly. And I think the main thing I want to say is that ask the question, are attitudes and technology changing fast enough to ensure that we can meet future energy needs sustainably? There's a long way to go. Past transitions took a long time, but major changes are happening. And I want to ask the question, are we approaching a tipping point? And I'm going to approach that first with a glass half full, half empty approach, and then a glass half full. So this is the glass half empty. If we look at the past, this is the percentage of world energy from different sources from 1850 up to almost the present. And there have been shifts, but they've taken sort of 50 years. This is global, by the way. I guess in North America and Europe, coal had overtaken biomass by about here sometime. So it's very slow. There's a huge infrastructure out there. That's at the same time as 80% we're trying to replace. It looks like it will be slow. Wind and solar are growing, but they're very small. On the other hand, the future is hard to foresee. I discovered these interesting statistics that in the USA in the year 1900, there were very, very few cars. But those that they were, steam was the winner. And I think on that basis, you wouldn't have, if you just said the future will repeat the past, you wouldn't have expected the internal combustion engine to be the winner, which it was in very few years, as you'll see in a minute. That's another one I'll skip. This is interesting. I already mentioned the UK without coal. This is the prediction of coal use of coal in China. Of course, these are percentages. Total is still going. No, the coal is starting to go down. This is a real change. It's a real change, and it makes you think that things can change. And here's an interesting one. Distributed power generation. These red dots are local wind farms. This is solar plants, and then there's biomass. There were about 30,000 installations in 2000. It's up to 1.5 million now. And here's an amazing thing. In the UK, which is not well known for sunshine, electricity in 2000 came from 1,000 sites. Today, actually, this is a year old, this figure, there are 850,000 solar installations in the UK. And on the 27th of May, last week at 12:30, solar produced 24.3% of the UK electricity. So change can be happening. Maybe we are approaching a tipping point. And I want to show you an example of a tipping point. So this is New York in 1900, and there's a lot of horses. Actually, if you look very carefully, there's one car there. This is 13 years later, cars. Actually, again, if you look very carefully, there's one horse and carriage. So change can be rapid, but I think there is a difference, before we get too carried away by this example, that cars, this was something new, and there wasn't an incumbent industry. Well, I guess there were, though the people are breeding horses. But it's not like power generation, where there's a very large incumbent industry there. Anyway, I think my last slide is whether we can meet future energy needs sustainably. Yes, but it will take a lot of time. I think it's too late to limit atmospheric CO2 to 450 ppm, at least at the price we're willing to pay. But we may be close to a tipping point. The energy landscape is changing very rapidly, driven by the falling costs of solar and wind. And to begin with, those costs were driven down by vast subsidies. But now they're on their own. They don't need the subsidies. It's the other guys who need the subsidies. So that's a big change, and that's one of the reasons I think that whatever your president says, there's such a momentum behind this change. It's just happening. These are getting cheaper. So I think these are great grounds for optimism. So I think we'll make it, but not as soon as I would like. Thanks very much. I'm sorry for going over time.
Thank you very much for a great presentation. Any comments? Andy?
I have a question. At a number of points, you had these goals that were set, like fuel efficiency of cars and other things that will be achieved in the future by, say, by a presidential decree or something.
I can't hear you very well, Nathan. Give him a microphone.
So at various points, there were agreements of something in the future. It depends on future technology that does not exist. For example, gas consumptions of automobiles. How are these numbers set?
In projections to the future? Which ones?
For example, there were some projections for the future, how efficient cars will have to be by a certain year.
Okay.
This based on this.
Well, that's just the law introduced by Obama, and I think the manufacturers can do it. They've shown they can do it in the past, but obviously in the end there will be some limit. And I think there's a point that I didn't go through that it was written on the slide. I think in the near term there's not that much technological uncertainty because technologies that are going to be deployed in the next 10 years must already be developed if they're going to capture a big market. So the uncertainties are in consumer acceptance and policies. As we go ahead, it becomes technologically much more uncertain, of course. But, I mean, you're a good point. We don't know about these predictions. I mean, some of them, you can go back. The only thing you can do, I used some BP predictions there. I have been back and asked, how did they do in the past? And that's quite interesting. There are many, and you can compare with others. There are about 10 or more bodies around the world that try to predict future energy use. And they're all pretty much in agreement. Could be they're all wrong, of course. But if you look at their past track record, the thing that is they're most sensitive to is their assumptions about the growth of GDP. And when they got badly wrong, it was because they didn't anticipate a slump, for example. On the other hand, in detail, they're very much wrong. So, for example, if you look, I have a slide of it, at the projections of the future oil and gas prices, they have to put them into their models, because when the International Energy Agency predicts future energy use, they have to assume something about the energy price. They're essentially uncorrelated with what happened. I mean, if you say they predict for the next 5 years it will go up, and then you toss a coin, you would have done better tossing a coin than you would by taking their prediction. But it doesn't matter because actually the use of oil in particular is extremely inflexible. Doesn't depend that much on the price. They've been completely wrong on solar power. I didn't show you that graph. They've totally underestimated the cost and the deployment of solar power, but up to now it hasn't mattered because it's been so small. But the big predictions have been right.
It's you made it clear, and it's been, I guess, clear. Is this working?
Yeah.
Yes, I can hear you anyway.
It's been clear for a long while, and you've made it beautifully clear that energy storage is a critical area. Could you comment on the various energy storage technologies, from batteries to flywheels, and where do you see the highest return on investment in research, or the greatest potential improvement and role of storage technologies?
Okay, so this is a slide, I don't know if you can see it now, that I skipped. I mean, right now, practically all the storage we've got is pumped hydro. I mean, that shows the breakdown. And by the way, that was built in the UK. We've got quite a lot of pumped hydro. And ironically, it was built, the biggest plant in Wales, was built in the early 70s to deal with the inflexibility of nuclear. You could take the nuclear at night and use it to pump water uphill and get it in the day. Now it's being used to compensate the flexibility of wind and solar. So there's been an inversion. So pumped hydro is big, but there's not that big a capacity to increase it. There's none in Long Island, obviously. No mountains around here. So one of the questions of the future is which side of the grid is it going to be? Is it going to be in your house or is it going to be central? And I think it's going to be probably both. I think in the house it will be a lot of lithium-ion batteries. Some of it may be in heat, actually. It's an interesting figure that UK domestic water tanks store 40 gigawatt hours. So this basically means to getting to timed heating, that we don't heat our water round the clock. You make good insulation and you store them and so on. A lot of it will be central, more pumped hydro, maybe compressed air, but it hasn't, there are people who've done it on some scale. Flow batteries, if we could get the cost down, because flow batteries decouple power and energy. I mean, you have a system where you put the liquid through it and then you put it into big tanks. So for a given power, which is determined by the size of the central system, you can add more and more capacity. But the trouble is it uses platinum. Now, I know people, I have colleagues actually, who are working on cheaper ideas for flow batteries, but I have no idea if it will work. I mean, I think I'm basically saying I don't know the answer to your question. And the big one for me is going to be power to gas for seasonal storage. I mean, turning electricity into hydrogen, turning it back into electricity, or maybe into ammonia. But there are other things you can do here. There's an interesting question which is in my mind to look at sometime. You can effectively use all the countries' freezers in supermarkets. If you had them under control, you said there's a sudden surge in demand, stop cooling the country's refrigerators. Okay? And there's a hell of a lot of energy in there. What I can't find, I can find figures for how much energy is going into keeping them cold. What I can't find is a time constant. Because the food regulation people will say, hey, you can't allow it to vary by more than 1 degree or something. So first of all, you've got to figure out, is that a reasonable limit from minus 15 or whatever it's at? But you could do it, if we could get the control of those things. So there are companies now that are thinking of selling such services. We will couple you, they could sell to the grid that they will provide a balancing service. So their market will be, they will tell the grid, we can guarantee to save you so much power on demand if you pay us enough. And then they will say to the supermarket, we will pay you if you let us have control of your refrigerators, and we guarantee it never change by more than 2 degrees. So there's a lot of novel ideas out there, but I honestly don't know the answer. The effort seems to be going into batteries, but that's been driven by cars. And of course, if you get into storing for the grid, different criteria. But for cars, it's all about it's the storage per unit weight. And that doesn't matter if you're just storing for the grid. So I don't know the answer. There are big battery systems. There's one which is selling balancing, big. There's a 10 megawatt company in somewhere called Leighton Buzzard in England, which is making money by tell the grid, you pay us and we can provide you extra power. You need extra power in sort of periods of a few seconds when suddenly the frequency is dropping and things like that.
I had 2 questions. First, you showed a graph of the future energy use in China, and you mentioned one curve that went up, which was not fossil fuels. What fraction of that is nuclear? What's
let's see. I showed that.
It was a previous graph you had. Yeah, there.
Here.
Yeah, right. Non-fossil fuels. Well, how much of that is nuclear? How much is other?
Actually, I'm sorry. I don't know the answer to that. I just found that preparing a talk a few days ago and thought that's an interesting slide for this purpose. I think it's probably. They're very, very ambitious plans for nuclear and solar, but the difficulty is the usual one. If those plans are telling you the percentage increase, but it's from a very low base. I can't answer it, but I can tell you where you can find that. You can find it on the web. Every year, the BP publishes what they call the Energy Outlook for 2035, and it's a very nice document which has beautiful graphics, so I tend to use their predictions. That's not one of their best efforts, but that's probably in there. I've probably lost the footnote, unfortunately.
Okay. Another question was on another graph you showed. in the terawatt hours and what fraction is. I guess this is International Energy Agency graph. You showed gas going up substantially. That was an earlier graph, about 20 slides earlier. So
in relation to what?
Versus the years.
Yeah, okay. That will be right back here. Yeah, it's probably, no, that's the beginning. Is it that one? No.
So on a scale of 1,000 and 2,000 terawatt hours per year, BNEF.
Electricity, was it? I don't remember showing that graph today. So you sure you're not thinking my other talk?
No.
School kids.
Anyway, my question had to do with the basis for the projection for gas.
How do they do those things? Well, I think when they look at future demand and they go around and talk to all the people, find out what they're investing in. So they do.
Well, this was also based on the fracking.
Yes.
It was, I think, reflecting the increase in gas due to fracking in the United States.
That was a U.S. graph. I know the graph you're talking about. It's that one, isn't it? This one?
Yes.
So natural gas going up?
Right. So
that's shale gas.
What's the peak? We speak of peak oil. What's the peak fracking time? Do you know?
Well, we don't really know yet. I mean, fracking, okay, that's gas fracking, but there's quite a lot of, this is electricity generation. If we just looked at oil production, there's a lot of fracking in that, of course, as well. So what was your question about fracking?
So the peak, how much, we've seen a substantial change in the U.S. reliance on fossil fuels, foreign versus domestic, due to fracking. And how...
I think the U.S. gas is, I've got it in another talk actually. There's a very large percentage of shale now in both oil and particularly gas. And it's large, and it's become, that's what's going to, it's very dangerous to predict the oil price. But I think that U.S. shale has become the swing provider now because you can invest in that stuff very quickly. So if the oil price goes up to $70, $80 again, you will see a vast number of new rigs going out, and that will cap the price. I personally think it's very unlikely we're going to go back to $100 a barrel or something like that. Don't know.
Trust British Petroleum to give you the right information?
British Petroleum, it's interesting because they produce these beautiful predictions, so they must make an assumption about the price. And everybody else, the International Energy Agency, MIT do predictions, the Energy Information Administration in the US, they tell you what their price assumptions are, but the oil companies don't. And I actually asked their chief economist, come on, how did you make this prediction about the swing? They were predicting the relative amount of shale and non-shale. So how can you do that without assumption about the price? He said, of course we can't. But if I, as a chief economist of BP, told you what I would think was the oil price, I would lose my job. So it's very odd. Some of the best predictions, we're working in the dark because they can't tell us because it's commercially sensitive. I think it's on.
I'm pretty disturbed by a bunch of things that our politicians seem to think and maybe that you seem to think. So first of all, hydrogen. The whole idea of the hydrogen economy and power and cars and buses fueled by hydrogen seems to me to be stupid because hydrogen is very unsafe and very non-dense in terms of volume, and if you make a high-pressure tank full of hydrogen, it's a bomb in every car. And if you make it instead of high pressure, you store it using chemical means, then you get very inefficient in terms of mass density storage. So hydrogen seems to be stupid for that purpose. And it seems to me that if you were to use hydrogen, a smarter way to use it would be to replace natural gas in, say, home heating and cooking industry. Another thing that disturbs me is electric cars based on lithium batteries, because lithium is rare, and the energy is actually coming from coal. So this is just a less efficient way to use coal. It just strikes me as a stupid development, but a possibly smarter development, which nobody seems to be interested in, would be the aluminum economy, or possibly the boron economy, where you use excess electricity from, say, wind when there's high wind to smelt aluminum. Then you use aluminum air batteries to power your cars, or as a very, very dense energy storage method. And for some reason, nobody seems to be interested in it. And another thing, if you want to know what research area would have the most impact, one of the answers that nobody's discussing would be high-temperature superconductors. If you could get room temperature, or even, say, minus 10 centigrade superconductor, that would revolutionize both the grid and energy storage, because you could store energy by making a big inductor, say, wrap some superconductor around a mountain. So,
okay, let me comment on a few of those things.
On that.
Let me take lithium first, because I happen to know the numbers. It's a very, very good point. If every car that was manufactured in 2015, every car in the world had been a battery car, it would have used 50% of the world's lithium reserves. That's the lithium which, the companies have their hands on, they know how to produce. It would have used 3% of the resources, the lithium they think is out there, but they haven't explored for it yet. So it's clear, and it's not enough if we really went all electric to have 1 year's supply. If your cars last 10 years, you can recycle it, of course. You've got to think about a longer period. I think that, but the experience always is that when metals become more and more in demand, people find more of them. But it is a serious issue, and I think that for lithium, there's going to be a really big premium on learning to recycle the lithium batteries, because you can recycle it. The problem is they come in different chemical mixtures. But of course there are sodium-ion batteries, and there's plenty of sodium around, so I wouldn't be too worried about that. As far as hydrogen is concerned, most of us, I've spent the early part of my life in an economy where the gas supply was hydrogen, and it wasn't causing huge problems, actually, so I don't see why it should again. And the classic example that's always given is that the Hindenburg aircraft blew up with hydrogen, but actually people say it wasn't the hydrogen burning, it was actually the material which was on the outside bag. So of course you've got to worry about these things, and it's dangerous. More or less everything we do is dangerous, but I don't see that as a showstopper. I do think there's been a lot of ridiculous hype about the hydrogen economy, especially back in the 90s. In this country there was a several billion-dollar program, we're all going to go to hydrogen, produced by people who didn't know what they were talking about. There was a colleague of mine from General Atomics who said that his congressman had said, or maybe his senator, said he'd like a demonstration of hydrogen power. So he took some apparatus along to his office in the Rayburn building or wherever it was, and so he took a car battery with him so he could make hydrogen with electrolysis. And the senator said to him, "What the hell's that for?" And he said, "Well, you've got to make the hydrogen." And the chap said, "God, I'd never thought of that." There were people out there, The Economist magazine thought of this, who seemed to think there were hydrogen mines. And that, they talk about the hydrogen economy as if you just go out and get hydrogen. So there are difficulties in all these things. I can't...
Produced from natural gas, so it's just a less efficient way to use natural gas.
There's an interesting question there of whether we can make it with... It is produced with steam methane reformers, as you say, from natural gas. But one of the questions is whether you could do it, actually do it by electrolysis. And that's rather expensive because the electrolyzers tend to have platinum in them. And it depends on the duty cycle. If electricity were free, so this extreme case, it's cheaper to make hydrogen with electrolysis, provided you're using the electrolyzer more than something like 35% of the time. So I think there's a real challenge to get the cost of electrolysis down. And one of the advantages for that, by the way, is if you had electrolysis makes very pure hydrogen. So it'll make the Haber-Bosch process, you could do it with lower temperature with different catalysts. So there's a lot of knock-on effects with these things. You've got to look at all of them together.
Okay, I think that we've had, I think he's been giving us quite a bit of information. So let's thank Chris again for a great set of lectures.